Hello guys, welcome to another QGIS tutorial. Now in this tutorial, we are going to show you how to derive a river network and the corresponding catchment area to that river network using a DEM with the help of QGIS. Now initially you can see that we have a DEM like this, and at the end of this exercise, you will learn how to derive the river network which looks like this and the corresponding catchment area which looks like this. So after you do the derivation, you will be able to find out how much is the contributing drainage area to this particular outlet, as you can see over here, and you will be able to generate the river network and the catchment area in the form of shapefiles. So without further ado, let's go ahead and get started with the tutorial. Alright, so to get started, first we will try to browse to the folder where we have saved our DEM, and from there first let's try to drag it and drop it into our working space over here. And before doing anything, I just want to first have a look at the current coordinate system, the current projection of this DEM. You can just right click over here and go to properties first. And under information, you can see over here the CRS is WGS 1984 geographic coordinate system. Now just keep in mind that it's absolutely essential that you first reproject your DEM into a projected coordinate system before you proceed with the tutorial. And also, if you would like to have a quick look at the current location of your DEM with respect to another base map, what you can do is you can go to Web Quick Map Services and go to OSM and OSM Standard, which will open up the standard OpenStreetMap for you. Now in case if you do not find this under the web option, the Quick Map Services is actually an additional plugin which you can install by going to plugins and then go to manage and install plugins, and from there you can simply search for Quick Map Services and first get it installed. And after you install that, you'll be able to simply add this OpenStreetMap to your working space as a base map. So relative to the OpenStreetMap, you can see that my DEM is actually somewhere in the middle of Malaysia. And now what I'm going to do is I'm going to actually transfer the existing coordinate system of this DEM from being a geographic coordinate system to a projected coordinate system. Now to do that, you can simply go to raster and go to projections, and from here we have one option called reproject. Yeah, so the input layer is going to be my DEM first, and from here the target CRS, the target coordinate reference system, you can actually set it to be your target coordinate reference system. Now in your case, if your study area is different, in your own respective cases your study area might be different, so just first find out what is the appropriate coordinate reference system for your case. For my case, I'm actually going to select this GDM 2000 Pahang grid, which is actually one of the projected coordinate systems used for Malaysia. So first I'm going to run, and then I can close this, and we have the reprojected DEM now. I can even go to this current CRS option over here, and from here change the coordinate reference system of the current data frame to be Pahang, to be GDM 2000 like this. And over here you can even get sort of a graphical view of where you have placed most of your data, and also for which geographical extents each coordinate system is actually going to be appropriate for. So I'm going to select GDM 2000 again and select apply and OK. So now both my data frame and the DEM are in projected coordinate system. Now I can actually go ahead and get rid of this DEM, which we will not need anymore. And I'm going to maybe rename this as reprojected DEM. Alright, now the first thing that I'm going to do is I'm going to fill the sinks of this DEM. Now in the original DEM there might be some sort of distortions with the presence of sinks, so what we're going to do is we're actually going to sort of correct the DEM by filling those sinks using one of the tools which comes under SAGA. Now the name of the tool is fill, so you can actually simply just search fill over here. Again, if you do not have this processing toolbox, you can just go to processing over here and activate the toolbox from here, and then it'll appear. And from here under SAGA GIS, you can select this the second option, fill sinks Wong and Liu, and the input for that process is going to be my reprojected DEM, as you can see over here. And these are the outputs which will be generated by this tool. Now for the time being, I'm going to untick this watershed basins and also the flow directions, because I'm going to actually take the things step by step. So let's only focus about this fill DEM part for the time being. And over here, either you can actually produce this as a temporary file, or you can just provide the specific path to which the actual file will be saved otherwise. Now for my case, I'm actually just going to open this up and save the file. This one I'm just going to name it as fill. Alright, after that we can run the tool, and it might take a couple of seconds for it to actually run the algorithm. Alright, once the process is completed, you can close this, and now you can see that we have a fill DEM. Now if you look at these elevation values, the elevation of the previous DEM was ranging from -5 up to 2165, but you can see that some sort of a correction has been now applied, by which the lowest elevation now is actually 1 meters above the mean sea level, and the highest elevation is 2101 as opposed to 2165, which is what it was before. Alright, so we won't actually be needing this reprojected DEM anymore, so I'm just going to deactivate that, because from here onwards we will be only working with the fill DEM, because now we consider this DEM to be sort of the corrected DEM. Now since our objectives are to generate the stream network, the river network, as well as the catchment boundary, now let's focus first on creating the stream network. Now if you would like to sort of get an idea about the existing stream network which can be derived based on this DEM, what you can do is first you can go to this processing toolbox and type Strahler Order. Now if you're not so sure about what Strahler Order means, it's actually something like this. As you can see, just imagine that this to be some sort of a river network, and you can see the blue color river lines are sort of the starting river lines from the mountain tops. And if you assume those to be the smaller streams, you can see that at locations where two small streams meets each other, it leads to the generation of a stream which has a higher order. As you can see over here, when two streams of order 1 meet, it actually creates another stream of an order which is 1 unit higher than the previous order. So as you can see, when 1 and 1 meets, it actually creates a new stream with the order number 2, and the same goes for stream with the order number 2 as well. As you can see over here, when two streams of order number 2 meet, it leads to the generation of or creation of a stream of order number 3. And one more thing to note is that if a stream with a lower number meets a stream with a higher order, there won't be a change in the stream's order. It actually retains the higher order of the streams. So the Strahler Order tool, which you can find under terrain analysis toolbox of SAGA, can actually do the same thing for you if you can provide the DEM as one of the inputs. So that's what we are going to do now. We'll open the tool first, and as the elevation raster we are going to provide the fill DEM. And the Strahler Order, I'm going to save this one to a file called Strahler Order, and we can run the tool. Alright, now after that you can go ahead and close this, and even the fill DEM for the time being I'm just going to deactivate. So what you see over here is actually a very dense network of streams with different Strahler orders. Now if you look at the legend over here, I mean the distribution of numbers, you can see that the lowest number is 1 and the highest number is 9. So the Strahler order varies from 1 to 9, which means Strahler order 9 can be generally regarded as streams which are actually larger in size, or larger in terms of the flow accumulations. The streams with the Strahler order 1 can be regarded as minor streams or very small streams. Now we can actually do a better visualization of the Strahler order of the streams than this. We can go to properties of the layer, the Strahler Order layer, and we can go to the symbology tab, and from here select single band pseudo color as the render type. And now from here you can see that we have two classes. Now what I'm going to do is I will try to select a color ramp which will be sort of more reflective of the color of a river, which is blue, and instead of using the continuous mode I'm going to split this to equal intervals like this. And from here you can see by default it gets splitted into 5 classes, whereby the lowest Strahler orders gets categorized in this light sort of blue shade, and the streams with higher Strahler order gets categorized in this dark blue. Now since we have the values ranging from 1 to 9, I'm going to split the number of classes also to be 9. Now this is not a necessity, but I think it's just a quick and easy way of sort of distributing the colors evenly, starting from 1 to 9. And after that, if you press apply, now you can start seeing very clearly which are the streams of higher order which can sort of be attributed to be large rivers in a physical sense. Also what you can do is you can just maybe zoom into one of those larger rivers, or one of those rivers with a higher Strahler order, and if you deactivate the Strahler order layer, you can see that it sort of reflects this real river. Over here there's one major river over here called River July. You can see that it sort of reflects that river quite accurately, along with other tributaries as well. You can see that as a whole this includes an entire network of rivers ranging from very minor streams all the way up to larger rivers as well. Now, if you want to sort of isolate only the larger rivers, something that you can do is you can go to raster calculator and you can assign the Strahler orders to be larger than a certain value. So I'm going to first specify the values of Strahler order, which means the value starting from 1 to 9. I would like to create a different raster, a different Strahler order raster, which will have values greater than or equal to, let's say, 5. Now, where does this 5 come from? I'm actually looking at the color distribution over here, or the Strahler order distribution over here. And I'm just picking something, let's say, from the middle. Even right now, I have no clue how this is going to look like. So what we can do is first define an output layer, and I will name this as Strahler order 5 just for the time being. And I can press OK to create the river network which has a Strahler order of greater than or equal to 5. Now you can see that it sort of isolates the major rivers, isn't it? If you would like to still sort of get rid of those these minor branches, what you can do is you can create another raster, and this time you can specify the Strahler orders to be a bit higher so that it'll sort of get rid of those minor Strahler order, those minor branches with the lower Strahler orders. Let's say this time we will set the value to be about 6 instead of 5, and I'm going to name this file as Strahler order 6. Here now we can export the file. Here now you can see that compared to the previous one, in this new file which has a Strahler order of 6 or greater than 6, you can see that it actually sort of isolates only the major rivers. And at the same time you can see that now the values are defined just by two numbers. It's either 0 or 1. So 1 refers to the streams or the cells, because just keep in mind that this is still a raster. You can see the pixels over here. So what I can do is I can actually I can try to put these values which are represented by 0 to be transparent. You can go to the properties and select single band pseudo color over here. Sorry, now I think we can go to select unique values from here, and then you can classify. And as you can see, we have two classes with value number 0 and value number 1. So for 1, which is actually the real stream network, I'm going to define the colors by color which is sort of a shade of a blue, something like this. And for 0, for the time being, I'm going to leave this color as it is. And if I apply, you can see that now the river network actually changes into a color which is represented by blue over here. And now I can go to transparency over here. And what I can do is, apart from this default no data value, I can also actually add a certain no data value. Now, if I put 1 over here, actually this whole river network will become transparent. So we don't want to do that. We want to make the outside areas transparent. So that's why I'm going to put the value of 0 over here, and if I apply now and click OK, and if I deactivate this Strahler order, you can now see that we actually managed to sort of derive the stream network in the form of raster still. And if you now zoom in, you can see that it more or less follows the main river, but in this lowlands, you can see that the DEM is actually less accurate. Somehow it still follows the major river, but when you go to these highlands, because the elevation variation of the DEM in these highlands are quite obvious, so that the derivation of the stream network is also quite accurate. As you can see, it more or less follows exactly, almost precisely the real river line in these cases, as you can see over here, but not so much in these lowlands. But that's alright. For the time being, I'm just going to accept this method. Of course, if you would like to have a much accurate delineation, you might have to work with a DEM which has a higher accuracy, like either IFSAR or LiDAR DEM. This is the level of accuracy that SRTM DEMs can provide. So I'm still going to actually proceed with this. Now let's see how we can export this into sort of a polyline. Now, even to do that, you can still use one of the tools of SAGA, which you can get by simply searching channel over here, and you can see the channel network and drainage basins. Alright, from here we have to provide a couple of things. To start with, we can provide the elevation. Now the elevation is still going to be my filled DEM, and over here as a threshold, specify the same threshold that we provided over here for the Strahler order. So that's going to be 6. As outputs, it actually generates a couple of things, but we do not want to have the flow direction, nor the flow connectivity or drainage basins, but we do want to have the channel. So I'm just going to leave that and deactivate the other things over here as well. Yeah, it's supposed to be this one. And over here, I'm going to specify the file name to be river network. And as you can see, the file type is already a shapefile .shp file. All right, now let's go ahead and run this. Alright, once the process is completed, we can close this. And now if I turn off all the layers and over here, and even I can switch off this channels layer, and as you can see over here now inside my folder there's a shapefile called river network. I'm just going to drag it and drop it over here, and now this is a shapefile, so we can do all the stylings that we would normally do with shapefiles, such as changing the color of the line and also maybe increasing the thickness. I'm just going to set about 0.46 should be fine. Now you can see that this is more or less the river network. So this is a file which you can quite easily pass to somebody else. Now before we finalize, let's go ahead and derive one of the watersheds corresponding to this network of rivers as well. Now from here you can identify clearly that this Jalai river is actually one of the biggest rivers. So I'm just going to select the corresponding drainage area or the watershed which contributes to a particular location along this river. I do have one area of interest. For example, let's say I would like to know, you can see over here there's one bridge crossing. Now I would like to know what is the contributing drainage area to the point of the river at this particular bridge crossing, and based on that I would like to demarcate the corresponding catchment as well. So for the time being, let's keep in mind that this is the sort of outlet that we are going to select for our derivation of the catchment. So let's go to the part of deriving the particular catchment for a specific outlet location. Now in order to do that, first we need to know the coordinates of our outlet location. However, you might be wondering right now, this is the real river network which the DEM identifies to be the river, but this OpenStreetLayers map shows the path of the river in reality. So this is something that we have to sort of accept and move on, because this inaccuracy is due to the resolution of the DEM. So what we can do is, ideally I would like to have this river line sort of exactly on top of this river Jalai over here, but since we do not have that, what I'm going to do is I'm going to create one point on top at the crossing of this river line and the road over here. Now just keep in mind that if you create your point over here, you won't be able to derive the watershed, because you actually have to create your pour point or the outlet location on top of the river cell. Now if I again turn on the Strahler order over here, you can see that the closest cell which corresponds to this bridge location is actually over here. So I'm going to create one point. So in order to create one point, you can go to layer and create a new shapefile layer, and I'm going to name this one as outlet. Well, the objective of creating this new point is sort of to extract the XY coordinates. Coordinate reference system, you can select GDM 2000 from here and click OK. Now you can see that we have one new shapefile called outlet. So now I can right click on that shapefile and go to and toggle the editing mode. And then we can go to this add point feature, and I can simply click over this cell and add a point. And I'm going to put the ID as, let's say, 1. Yeah, that's about it. So now I can just click over here and save my edits, and now you can see that we have a new shapefile with a point at this particular location. So I'm going to, let's say, have a look at the attributes table. Now ideally I would like to actually extract the X and Y coordinates into 2 different columns. So you can simply do that by going to the field calculator over here, and I'm going to create a new field by the name X coordinate. Let's say we shorten the name to be X coord, and over here you can go to geometry and you can find this X, this $X. As you can see over here, it returns the X coordinate of the current feature. So I'm going to double click on this one. Well, the output field type, maybe it's better to change it to decimal number so that it'll contain a couple of decimal points as well. Well, 3 in this case. Alright, now click OK. Now you can see that it actually extracted the X coordinate for us. And similarly, we can extract the Y coordinate as well. You can go to the field calculator and put the field name as Y coord and go to geometry, $Y, and click OK. Alright, now you can see that we have the X coordinate and the Y coordinate, and we can click on this toggle editing mode again to save our changes. Now to actually derive the contributing drainage area, or in this case we also can call that as the catchment area, we can go to one of the tools called upslope area, which also comes under the terrain analysis toolbox of SAGA. So we can double click on this and leave the target area since it's an optional input. And the target X coordinate and the Y coordinate, I'm going to open this outlet again, the attributes table of the outlet. And what I'm going to do is I'm going to simply copy the cell content and paste it over here. Similarly, I can copy the Y coordinate and paste it over here as well. Just Control V over here. And the elevation, again, we have to select the field DEM. And the rest of the items we can leave it as default. And the upslope area I can, for the time being, I'm actually just going to let it save to a temporary file. And we can run this. Now if you close, you can see that it actually managed to delineate the contributing catchment like this. Now if I move the river network on top of this, since we have the river network shapefile, you can see that this particular catchment is basically created by this river network over here. So if you're unfamiliar with the concept of a catchment or a watershed, so let's say just imagine that there's a certain amount of rainfall that's happening over here. All the rain that's actually falling on the white area will be flowing into this particular region, and all the rain that's actually flowing outside of this white area will be flowing to other particular catchments as well. So that's how basically the concept of the catchment works. So it's basically catching all the rainfall that falls on this white color area, basically drains within this particular area into this outlet over here, which we specified. So I guess we have almost completed most of the things that we need to do. Now, just keep in mind that this is still a raster. So we can convert this raster into a polygon as well. So the way to do that would be you can go to raster and conversion. From here, you can select raster to vector. And my input layer now is going to be the upslope area. The rest we can leave as it is, and just that we can save this, since this is going to be a permanent file, we can save this to be .shp, a shapefile, and the file name is going to be catchment area or the catchment boundary. Alright, now we can run. Once you run this, I can now go ahead and deactivate all these other unnecessary parts and maybe move this outlet to be the top layer so that it's kind of clear for you guys where the outlet exactly is. And now if I open this, let's get rid of this one. And so as you can see over here, when I navigate to the place where I saved the file, you can see that we have a new shapefile called catchment boundary as well. I can simply drag it and drop it over here. And if I go to the attributes table of that catchment boundary, you see that we have two attributes. We have one by a DN value of 100 and the other one which is sort of the outside area. So what I can do is I can simply turn on the editing mode. And I can select this outside area and simply hit delete. So that will sort of delete those unwanted parts of our catchment, of our shapefile. And then I can save the edits. So that sort of isolates all the relevant areas to us. I'm going to move this river network again on top of this. Now to make this visualization a bit more clear, what I can do is I can clip this river network by the corresponding boundary of my catchment area. Now I can do that simply by typing clip over here, and I can go to polygon clipping option under the SAGA GIS tools as well. And I would like to clip my river network by the boundary of my catchment, and I can simply run this. Alright, now if I turn on this river network and I forgot to specify a name for this, you can see that now it has actually been clipped to the boundary of my watershed. Now let's do a couple of changes. First, let's export this into a proper shapefile. S3 shapefile, and this coordinate reference system is correct. And I'm going to save it at the same location. This one I'm going to name it as maybe river network clipped.shp. The rest we can leave them as it is, and I will get rid of this previous layer. And maybe I can do a bit of styling, change the color again to be blue, and increase the size to be 0.46. Now, as you can see, we managed to derive the catchment area as well as the river network, which corresponds to this particular outlet. Now, if you would like to maybe get rid of the fill color, you can do that as well. You can say outline and maybe only increase the thickness of the outline. So I guess that's about it for this tutorial. If you do have any questions regarding the process that we followed for this tutorial, do comment them down below. And now you can see that we can actually pass these layers onto someone else as separate shapefile layers for the catchment, which corresponds to the catchment area boundary as well as the river network within our derived catchment as well. So I guess this could come quite handy, especially in studies related to hydrology. So before we wrap up the tutorial, I would like to again remind you guys, if you haven't subscribed to our channel, please do so. If you do find these tutorials quite valuable, then don't forget to subscribe as well. And I'll see you guys soon in the next tutorial.